Gauss-Miss the prime expansion gap.
Here we're going to introduce the prime expansion gap. Now what does that mean? Well, we've got prime vectors. What does that mean? Here we've got clock math. 12 is the magic number, 12. And we know that primes are only at 1 o'clock, 5 o'clock, 7 o'clock, and 11 o'clock. The prime vectors are 1 o'clock, 5 o'clock, 7 o'clock, and 11 o'clock. Now you add 12 at 1 o'clock to get 13, add 12 to get 25, keep adding 12, and you get all of the numbers associated with 1 o'clock. Same thing with 5 o'clock. Add 12 to get 17, add 12 to get 29, 12 to get 41. You keep going, you've got all of the numbers associated at 5 o'clock. And this is called clock math. Or the mathematicians like to think of it as modular arithmetic. Now at 1 o'clock, we've located all of the primes and we've put them in yellow. And you can see that every number would be prime except that primes combine to create composites. In order to recognize the pattern of the primes, you need to pay attention to the simple stuff. Mathematicians for thousands of years have missed the pattern of the primes because they didn't pay attention to the simple stuff. Here's the simple stuff. 5 is a prime. Now, most mathematicians will say any number ending in 5 or 0 is a composite, so forget about it. We're not going to forget about it. We're going to learn something from the number 5. Here we are. 5 is a prime. 5 times 5 is 25. We know that we go counterclockwise to get to 35, which is 5 times 7. The multiplier here is 5, so to get from 1 o'clock to 11 o'clock, counterclockwise, there's a difference of 2. So we add 2 to the multiplier, we get to 7, we've got the next composite. That is the pattern. We want to start the pattern at perfect squares. Start the pattern at the perfect square of 11 times 11. Start the pattern at the perfect square of 7 times 7. Start the pattern at 5 times 5, a perfect square. So primes squared start the cycle. Now we already discussed in a previous video this pattern of going counterclockwise. There's another way to discover the pattern of the primes, and that is by looking at the prime 5, multiplying it by 12, since we're in clock math, getting 60, get to 25, which is 5 squared. You add 60 to that, you get to the next composite. Add 60 to that, it's off the board already. You get to the next composite. Same thing here. Add 84 to 35, and you get to 119. Why did we add 84? Because 7 times 12 is 84. 7 is a factor. 7 is a factor here. So we add to 35, 84, and we get to 119.
This board shows us modulo 12, where we can use simple addition to discover new composites. At 1 o'clock, which is vector 1, we can move quickly to 25, which is where 5 first appears in vector 1. 5 times 5 is 25. Now 5 times 12 is equal to 60. So the prime expansion gap for the prime number 5 is equal to plus 60. So at 25, we add 60 to arrive at 85. We add 60 to 85 to arrive at 145. We add 60 to 145 to arrive at 205. By adding 60 to each of the composites related to the prime number 5 at 1 o'clock, we will locate successive composites indefinitely, up to 1,000 digits, 2,000 digits, 10,000 digits. Now let's look at 5 o'clock, also known as vector 5. At 5 o'clock, we're going to look at the prime number 7. It first appears at 5 o'clock at 77, which is 7 times 11. 7 times 12 is equal to 84. So prime number 7 is equal to the prime expansion gap plus 84. So we will add 84 to 77 and get to the very next composite, which is 161. We add 84 to 161 and we arrive at the very next composite, 245. We keep doing this and we will arrive at all of the composites related to the prime number 7 at 5 o'clock. Let's look at 7 o'clock, also known as vector 7. The first time the prime number 13 appears is at 247. 13 times 12 is equal to 156, so that's the prime expansion gap. At 247, we add 156, and we get to the very next composite related to the prime number 13. That's 403. At 403, we can add 156 to get to the very next composite, which is 559. We keep adding 156, and we will discover all of the composites related to the prime number 13 at 7 o'clock. Let's now look at 11 o'clock, which is also known as vector 11. The first time 17 appears, the prime number 17, is at 323. 17 times 12 is equal to 204. Beginning at 323, we add 204 and we arrive at 527. We can add 204 to 527 and we arrive at 731. We can keep adding 204 each time to the composites, and we will progress further and further down the number line at 11 o'clock, discovering all of the composites related to the prime number 17. The prime expansion gap for each prime remains the same for each time of the day where primes are discovered. For example, the prime expansion gap for 17 is plus 204, and wherever 17 shows up, you can add 204 to arrive at the very next composite.
So the prime expansion gap shows you the gap between composites. That gap you can discover by just adding. You add whatever the prime is times 12. 5 times 12 is 60, you add that. 7 times 12 is 84, you add that. And you can see that here. We add 84 to 35, we get to 119. So the pattern of the primes becomes very obvious if you slow down and examine each number in clock math. 1 o'clock, 5 o'clock, 7 o'clock, and 11 o'clock, that is where all of the primes will be located. But you have to eliminate the composites, which are in blue. And now, looking at this board, you can see how easy it is to discover the composites and how easy it is to discover the primes.